And please feel free to start whenever you are ready. Thank you very much.
Okay, thank you very much for kind introduction. It's my big pleasure to give a talk here, and I will try to explain about the relation between right-angle polyhedra and hyperbolic space and some applications to hyperbolic nodes. And first of all, I would like to congratulate Lou with his birthday. And you can see the photo. We are very glad that Lou visited Novosibirsk for 3 years. It was a big grant, and we collaborated with him. This picture near the Institute of Mathematics, we have Institute of Genetics, and there is a monument devoted to mouse who producing DNA. And it was picture where Lou is near this mouse producing nodes. So many best wishes to him. So I would like to tell about right-angle polyhedra, and after that to discuss some applications of volume bounds. And I will go to generalized hyperbolic polyhedra, and next to volumes of highly twisted nodes and links. And finally, I would like to discuss some results about volume determinant conjecture for highly twisted nodes and links. So we are interested in geometry of hyperbolic three-dimensional space. So let's H3 denotes hyperbolic free space. And we can see the polyhedra in this space. And we say that polyhedron is right-angled if all its lateral angles is pi over 2. It's similar to Euclidean cube, but in hyperbolic case, polyhedra are much more complicated. And also we say that polyhedron is ideal if all vertices are ideal, so it means that all vertices belong to boundary of the hyperbolic space, or absolute, sometimes we say it. So we consider this class of polyhedra, and the existence in Newton's theorem was proved by Andrei in 1970. He considered acute-angled polyhedra and having finite volume, and he proved necessary and sufficient conditions for existence of polyhedra in hyperbolic space for this family. And I give here only particular case which related to ideal and right-angled polyhedra. So if you have a combinatorial polyhedron, that then we can realize it in as a ideal right-angled in hyperbolic free space, even only if there are some satisfied some combinatorial conditions. So each vertex is foreign, and there are no non-trivial for circuits. So you consider the surface of the polyhedra, you consider the circuit, and you say it's for circuit if it intersects exactly h edges for edges of the polyhedron, and it's say not trivial. It's not around one vertex. It is separate two regions. So this combinatorial condition, and also Andreev's theorem states that this realization is unique up to the isometry of the space. And since we working with polyhedra, we have standard results. For example, the famous early formula for polyhedra, saying us that the number of vertices minus number of edges plus number of faces equal to 2. And we can see the following situation. So double number of edges equal to 4 times number of vertices. So we easily see that number of faces is equal to the number of vertices plus 2. So we can characterize number of vertices or number of faces. It's very similar. Also from the early formula, we obtain some relation between number of polygons with different number of with some number of faces. For example, we easily obtain the relation with number of triangles is 8 plus something. So we conclude that such polyhedron always has at least 8 triangular faces. And this case realizes if you're working with octahedron. So I regard that combinatorial octahedron, just a polyhedron, when you have 8 faces and all of them are triangles. So we have such conditions, and you consider the class of all ideal rectangular polyhedra and denoted by IR. And I just recall that in the case of hyperbolic geometry, to find volumes or to express volumes, we use Lobachevsky, after Lobachevsky and after Milner, we use a function which called Lobachevsky function by Milner, and it's presented here. It's kind of the logarithm, and you see the picture of this function, and it's very useful. And I will use few constants related to values of this function. For example, if you consider free Lobachevsky function calculated in pi over 3, you'll get something like that. Just the first digits. Just approximation. So this number is just a volume of maximal ideal regular maximal ideal tetrahedron in hyperbolic space, and is a regular tetrahedron, so it's a volume of ideal regular tetrahedron in a hyperbolic free space. So it's in contrast with Euclidean geometry. Here volumes are bounded by this constant. Volumes of tetrahedra, I mean. Okay, so it's constants which I use later. And what about examples? So we discussed that the simplest example having just 8 faces is octahedron. And you can consider octahedron just like a kind of antiprism when you have triangular top and triangular bottom, and you have 6 triangle faces between them. And you can easily extend this idea to a family of polyhedra, call it antiprisms. So antiprism with the parameter n, usually such a picture, you have angle top and angle bottom, and triangles between them, and picture presented in the top of the slide. So you have antiprism with trigonal base, with orthogonal base, and so on. So this family called antiprisms, and this family satisfies conditions of the existence theorem. So all vertices are covalent, and if you consider any circuit on the surface, so it intersects more than 4 edges if it is not trivial. And this family was considered by William Thurston in his famous lecture notice. He constructed some links from link complements from this polyhedra, and he calculated the volume. So a volume of elements of this family can be expressed according to formula presented here. So if you have n antiprism, so you use the Lobachevsky function to find the volume. Formula is given here. And for example, if you consider octahedron, so you'll get just some constant, which we the volume of the octahedron is 3, 6, 6, and so on. So it's just approximation again. Okay. And what about other polyhedra in this family? There is a very nice transformation, call it H-twist transformation. It's combinatorial, and let me describe this transformation. So suppose you have polyhedron, which is ideal rectangled hyperbolic space, and suppose we have some face, fixed some face, and we have 3 edges going consecutively. So for example, the E1, E2, and E3. So what is the H-twist transformation? It is the following. You can split it in 3 steps. Firstly, you delete H, E2, you delete you delete each E1 and E3, and you create a new vertex. Let's call this vertex V. After that, you connect this new vertex with terminal points of the edges. That's printed here, and you obtain a new polyhedron, and it is a polyhedron which still has 4 valent vertices, and it has property about non-trivial chord circles. And the example presented here. So if you start with octahedron, so A3, so there is no possibility to have such transformation. But if you start with A4, so you see there is H and E1 and A3. You can use each twisting transformation, and you get new polyhedra with the vertex V as presented in the third picture here. So this transformation can be applied. It's combinatorically, but what is important, it can be realized geometrically in the sense that we obtain hyperbolic polyhedra. And this let us look at the example. So if you start with antiprism with number 6, you can apply this procedure with twisting operation and you obtain a new polyhedra. Let me call this new polyhedra antiprism with twisted antiprism with annotations by star. So we can still, since we know volume of the antiprism, we can find the volume of the twisted antiprism. It's just a sum of volumes of antiprism of the previous step and octahedron. So we can construct such a family, and we are able to calculate volumes. And the role of antiprisms and H-twist transformations is clear from the following combinatorial results. So people from graph theory, Brickman and his co-authors, they considered this H-twist operation to construct new graphs, new planar graphs, and they observed that you can obtain polyhedra from our family combinatorically if you consider antiprism and twist H-twist transformation. So any ideal rectangular polyhedra is a antiprism or can be obtained from some antiprism by a finite number of H-twist transformations. The results were obtained for graphs, so they didn't use hyperbolic geometry, but in virtue of Andreev's theorem, we can state about hyperbolic geometry of this polyhedron. And this result was improved by Nikolai Erchovets in 2019, and he observed that any polyhedra from our family is an antiprism or can be obtained by H-twist transformation just from A4. So don't necessarily to use all antiprism for H-twist transformation, but the A4 is enough. You can get everything from this one. These combinatorial results. But we are interested in vol, in construction of this initial family of polyhedra, and this diagram present the initial list and each test relation between them. So you see in this picture you have antiprism denoted by red, the point by red, and the twisted antiprism denoted by yellow. So there are natural relations between them, since twisted antiprism can be obtained from standard antiprism by H-twist transformation. And after that, you can go ahead to obtain new polyhedra, and you can see from the diagram that where is not unique, you can obtain one polyhedra from different ways, starting from different initial antiprism. And also, to support Hertz's theorem, you can see that if you take antiprism with number 4, this antiprism number 4, you can obtain everything except antiprisms. It's just an illustration of the result. Okay, so we see that there's some kind of very strong rigidity. So everything depends of a number of vertices and combinatorics. And it's natural to ask if you can estimate volume of polyhedra combinatorically. For example, if you know number of faces, or if you know number of vertices. And first results in this direction was obtained by Christopher Atkinson in 2009. He proved the following. So if you have a polyhedra, which is ideal rectangled, so is ideal vertices and all the angles pi over 2, and if a denote number of faces, so the minimal number is 8, so it's f is at least 8, then we have a lower bound and upper bound for the volume of the polyhedra. And you see the bound is a linear in number of faces, and I just mark it by red, the constants which you already discussed. So weak opt is just constant, which special value of Lobachevsky function. And this result was lower bound, upper bound was obtained, and after that we started to investigate how explicit are these bounds. And we found that we can improve this result if we fix some number of faces a little bit bigger than 8, so you just consider the initial part and let's go ahead. And we can improve the upper bound if you consider polyhedra with at most 11 faces. So you see that again linear function, and the coefficient, angle coefficient of this function is asymptotically exact. So we have possibility to improve only the free coefficient. So we improve it upper bound, and let me show how it looks. If you start to calculate volumes, so there is one line is number of vertices, and second coordinate is the volumes. So the points here, they present volume values for polyhedra, and 2 lines is a low bound by Atkinson, and upper bound obtained by our theorem shape just presented. So we start from number of 11 faces, so 9 vertices. So this bound. And you see that this bound, low and upper bounds, the really bounds, but maybe not so nice. It can be improved, but it's difficult to improve the since we calculate volumes or approximately. And also you see isolated points in these columns. So these points correspond to antiprism volumes, and we discuss it later. Okay, and we can improve a little bit this upper bound if you go ahead with the number of faces, and we obtain it jointly with Stepan Alexandrov, Nikolai Bogachev, and my student Andrei Yegorov. So if you consider a case where number of faces is more than 26, that again you can improve the upper bound. So if you have upper line, and you just you cannot change the angle of this line, you can just go ahead and to change the constant for this line. Okay, so this theorem presents several cases when we can improve the bound. For example, if you have a number of faces more than 26, or if you know that there is some k-gonal phase, if k is big, then you get better bound. And another possibility, if your polyhedra has only triangular and quadrilateral faces, and number of faces is more than 70, so again you can improve this bound. So this illustrates how you can obtain an upper bound for different situations if you know combinatorial properties of your polyhedra. And you can ask about the initial list of ideal rectangle polyhedra, so we can find them. So using Atkinson low bound, if volume of polyhedra is less than 5 times volume of octahedron, then the number of faces is less than 24. So we tabulated all this polyhedra, and they found all their volumes, and we found that there are only 248 different volume values for polyhedra such that volume is bound by a constant 5 times volume of octahedron. And just an example, you can see two polyhedra. One has a minimal volume among all polyhedra with 23 faces, and another has the maximal volume. So, and you see both of them are bigger than 5 times volume of octahedron. And we have got some conjectures about minimal values. These conjectures based on numerical calculations for polyhedra with at most 23 faces. So conjecture says that if a number, so you can see the minimal volume polyhedra among all ideal rectangular polyhedra in hyperbolic space with n faces. So conjecture is if n is even, so the minimal volume polyhedra is acting antiprism. What you see in the figure. as isolated vertices. And if an odd, then minimal conjecture says that minimal volume attached to twisted antiprisms. And since formula is very complicated, we can state only that conjecture is correct for number of faces at most 93. It's difficult to understand what happens after that. But it seems it's true, but very difficult to prove, technically difficult to prove. And also, I want to present you some results. Not, of course, not all values, but just to give idea what is how many polyhedra, how many different volumes, and what is minimal, what is maximal. So the first column just number of faces of polyhedra, and second column just the number of polyhedra, and the third volume is number of different values of volumes. So you see, for example, for the last line 33, there are more than 72,000 of polyhedra, but just 13,000 of volumes. So you see that many polyhedra has the same volume, and it's natural to ask why. And let me show just one example. Two polyhedra with the same volume. One has 14 faces and another has 13 faces, and volume is about 10. And from this particular example, it's easy to see that you can split one polyhedra in two pieces and rearrange these pieces and construct a new polyhedra. So it's called kind schizoid congruence, very famous equivalence of between polyhedra, which goes back to the third problem by Gilbert, when he asked under which conditions two polyhedra are schizoid congruent. Of course, they should have the same volume, and it's very famous that the conjecture is solved in the case of Euclidean geometry, but it's still open in the case of hyperbolic geometry. And still, since we have many examples of polyhedra, it is a natural problem to try to understand which ideal rectangular polyhedra are schizoid congruent. So you know this pair, and there's some other pairs, but we don't have general description. And of course, volumes should be the same, but what else? Maybe then invariance, no, maybe enough, maybe not enough. So it's case of hyperbolic geometry is complicated in this sense. And to demonstrate why we consider ideal rectangular polyhedra and why this family is so important, let me discuss maximal volumes of generalized hyperbolic polyhedra. And it's related to the conjecture, which is kind of volume conjecture. And of course, everybody knows the volume conjecture due to Kashaev, Murakami, which relate Carl-Johnson invariants and volumes of nodes. And similar conjecture was formulated by Konstantinov, Goritao, and van der Wien for graphs, for planar graphs of polyhedra. So they defined invariant, which is analogous to Rye-Furrow invariant for free manifolds, but now they constructed it for plane graphs, but they denote it again TV, sending out to Rye-Furrow. And let's consider Rye-Furrow invariant for plane graph gamma, and R is positive integer, which give us possibility to define family of invariant invariants. I don't want to define here, just give you idea that it's very similar to invariant for free manifolds. Use similar state sums, but definition is quite long. So they conjecture the following. So suppose we have a graph. Here graph gamma, and it's a free connected planar graph because we want to be one skeleton of polyhedra. And the conjecture is the following: if R runs over all the integers, if you consider limit when it goes to infinity, and if you consider logarithm of Rye-Furrow invariant and divide by R and multiply by pi, so you get something in the mirror limit, and the conjecture is you'll get the maximal volume over all hyperbolic polyhedra which have gamma as a one skeleton. So, for example, you fix combinatorics of tetrahedron, you consider all hyperbolic polyhedra which combinatoric are tetrahedra, and what is the maximal volume? It's all built on the right part of this equality. And what I want to remark here, so we consider polyhedra with finite vertices, infinite or ideal vertices, and also consider so-called ultra-ideal vertices, so which are out of hyperbolic space in some projective models. And in this case, we consider truncation of the corresponding vertices. Let me show, say, the relation between this conjecture and our ideal regular, ideal right-angle polyhedra. So we can ask what is the right part of this equality, what is this supreme volume, and we already proved quite recently that this supreme is exactly volume of some polyhedra which he called rectification. So we have, let me explain what it means. So suppose we have a tetrahedron in the projective model hyperbolic free space, and you have a vertex, and if your vertex is finite, so it's a standard tetrahedron which you can imagine. If it is infinite vertex, if ideal, so it's you can see the cusp if you in your tetrahedron. And the most interesting case, if you have ultra ideal vertex, so it's out of the ball of your model hyperbolic free space, and in this case your polyhedra is not belong to hyperbolic geometry wholly, but what we can do, we can truncate tetrahedron, so we consider the polar the plane which polar to our vertex, and you consider truncation, and it's called generalized tetrahedron tetrahedron in hyperbolic free space. And we can of course generalize the idea for arbitrary polyhedron, and it looks like something like that. So suppose you have a tetrahedron combinatorically, yeah, and it's can have finite vertices like to present in this picture, or maybe two other ultra ideal. So in this case, you consider the truncations of your polyhedra, and these truncations belong to hyperbolic geometry. And the yellow picture at the top shows that you truncated faces, vertices of tetrahedron, so you get another polyhedra, and if all vertices are truncated, you will get a polyhedra which is presented here in the central red figure. So all vertices just orient vertices which are ideal, and you have polyhedra with ideal vertices. And since you truncated by orthogonal places, so your faces will meet with angles pi over 2. So finally, you obtain polyhedra which has ideal vertices and the angles pi over 2. So it's exactly belong to our family of ideal angle polyhedra. And its volume is called the volume of rectification. Okay, and in the case if you consider just tetrahedron, I would like to show you the picture of volumes, the figure of volumes, and it was due to Akio Shijima. And you see here that 0.pi over 3, this corresponds to the ideal regular tetrahedron when all the angles pi over 3. And if you go to the smaller diagonal angles, so you write finally to a polyhedron which is combinatorically octahedron. So the volume is presented here. So the maximal volume is just volume of octahedron, so 8 Lobachevsky functions populated in pi over 4. So this is equal to 3.66. So now we admitted truncations, so I obtained bigger polyhedra, and the limit is the limit value corresponds to ideal rectangle situation. And since we have ability theorem about maximal volume, and we have since we have our upper bounds, so we can conclude what is the upper bound in the case of generated hyperbolic polyhedra in terms of number of edges, because edges will correspond to vertices in a rectangle polyhedra. So these are upper bounds. And if you have more information about combinatorics of polyhedra, if you know number of trivalent vertices, and if you know a number of triangular faces, we can prove these bounds like presented here. And now I would like to discuss the applications to nodes and links. And let's consider the following approach. If you have a diagram of node or link, so you can talk about twist regions. So twist region is the maximal sequence of twist in two strings in the diagram, or in other words, just the maximal sequence of bigons. And let's denote by T of diagram D the number of twist regions in this diagram. And just example of a diagram of some node here. And you see there are three twist regions, three sequence of maximal sequence of bigons. And these combinatorial parameters of the diagram is very useful. And it was used by Lakenby, Egel, and Dylan Thurston to obtain an upper bound for the volumes. So if you know a diagram which is reduced, just reduce it. So upper bound can be presented as 10 times the volume of the maximal volume of the tetrahedra, and 10 times number of twists minus 1. And this very useful upper bound. And fortunately, we can improve it in the case if number of twists is big enough. So usually people call it highly twist nodes. But how high? In our case, if you have more than 8. So if you have more than 8 twists in your diagram, then we can improve the Lakenby-Egel-Thurston upper bound. So instead of number of twist regions minus 1, you can put a number of twist regions minus 1.4. It's just let me tell the idea of the proof of Lakenby results, and similar to our proof. And let's start with the diagram. So you have three twist regions, and if we construct augmentation of this node, it will be link, and we replace each twist part by a new component represented here by red. So we have, in this example, we have three twist regions. So we create three new components which presented here by red as a polyt vertical, and it's a standard result that the node can be obtained by the integers from this augmented link. So we have the upper bound for the volume of the node is bound by the volume of the link. And after that, we can use idea from Lakenby, Egel, and Dylan Thurston to we decompose link complement in two equal ideal rectangle polyhedra, and this is just very schematic. I'll explain it how we do it. So we replace it. You can think that we replace each component, each additional component by a pair of triangles. So it's three punctual spheres really, and after that we shrink black edges which are parts of other components of link. So we since we interested in complement, this shrink can give us new vertices of polyhedra. So totally we have some collection of red vertices which came from additional components of during the augmentation, and you have black, which correspond to edges of diagram of the link. And it's easy to see that the number of vertices of our polyhedra will be 3t, so t red and 2t black. And also we see that we have more than 2t triangular faces. And since complement constructed from 2 copies of polyhedra, we have upper bound, so volume of the node is bounded both by 2 times the volume of polyhedra. And after that, you just calculate very carefully the upper bound for the volume of polyhedra, similar to the previous discussions for ideal polyhedra. So it can be, as I told you, in the case of highly twisted, it can be proved. And finally, I would like to say some words about the volume determinant conjecture. And let me recall this conjecture was formulated by Champagny-Karl Kaufman in Parcel. And it states the following. So let K be an alternative hyperbolic node or link. Then we have the following inequality. The volume of the node complement is bounded by 2 pi times logarithm of the determinant of the node. The determinant can be defined in different ways. So it's the determinant of Seifert, so some metric corresponding to Seifert surfaces, or it's just the order, the first homology group of two-fold orange cars. There's a lot literature about the determinant. It's very famous invariant. So firstly, Karl Kaufman and Parser observed that this constant 2 pi is accurate. So if you take something smaller than 2 pi, some alpha smaller than 2 pi, then you can find such node that inequality fails. Also, they prove the conjecture. They check the conjecture for some families of nodes. So for example, for alternating hyperbolic nodes, admitting diagrams with its most 16 crossings, so for tabulated nodes, and for a few, infinite families of nodes of special type, called waving nodes. After that, Barton proved this conjecture, that the conjecture is true for 2 bridge nodes and for nodes which are closed of braids on 3 strings. And I would like to mention the result of Stoyanov, which is very close to this discussion. So he proved the following inequality. So volume of non-trivial, not splittable alternative link is bounded by the following expression, where I have some constants and use a logarithm of determinant. It's not exactly the same as the volume determinant conjecture, but it's very close. And what is the idea? How to prove? How to Barton, for example, prove it his result? So you're interested in a lower bound for determinant and for upper bound for volume. And Barton used the following idea of Stoyanov. So he bounded determinant from below by some expression which can be done in terms of number of twists. So we have determined bounded by 2 times gamma in degree number of twists minus 1, where gamma is just some constants which can describe it as a root of equation presented here. Then Barton obtained next step inequality. We determine bounded below by this gamma in degree of number of twists regions minus 1 plus number of crossings minus number of twist regions. And finally, he obtains the following inequality, which relate number of crossings, number of twists, which guarantees that the conjecture is true. So he proves that you have such inequality satisfied, then conjecture is true for such a node. And the proof is based on the Stoyanov result for bounding of determinant, and it also used bound for volumes, which was done by Luckenberg, Egel, and Thorsten inequality. And since we are able to improve lacking the Eggleton inequality in the case of highly twisted knots, we also can improve bound obtained by Parton. In the case of twist regions bigger than 8. And we have two ingredients here. The first is a result proved by Ito. It is still preprint in archive, as I know, so I mentioned 23 plus, it is 23 archive. So he obtained a low bound for determinant as presented here. So you see this bound use the number of twist regions TD. And by applying this bound and also our upper bound for volumes for highly twisted regions, we obtain the following inequality. So if this inequality presented in theorem 6 is satisfied, then the determinant volume conjecture is true for such a knot. And we have few constants here. It's maybe looks complicated to understand is it good or bad. So let's compare Barton results and these results numerically. So if you look in Barton's theorem, and for example, take number of twist regions equal to 9. So we're interested to compare if bigger than 8. So let's set equal 9. So the Barton theorem states that the volume determinant conjecture is true if number of crossings more than this constant for 400,000. And if you apply the theorem 6 presented on the previous slide, so you obtain that in the case when number of twist regions is 9, so then the volume determinant conjecture is true if number of crossings is bigger than 37, so more than 37,000. So I understand this balance is quite far from what we want to obtain. So as I know, up to date we have this conjecture proved only for initial list of tabulated nodes, for two-bridge nodes, for links obtained by exclosures of free-string braids, and only these results for highly twisted nodes. So thank you very much for your attention. Maybe I can stop here.